of IC 61850. Then we'll talk about digital substation as more than just the 61850 and the rationale why we need or would like to have digital substation capabilities, and proceed from there to talk about other advanced concepts. Next, please. Okay, so the first thing you'll find if you go out and try to look for a formal definition of IEC 61850, that there really isn't one. In articles and papers and publications referring to digital substations, what you'll come across many times is that they'll say that if a substation is based on Ethernet local network communications and has IEC 61850, then it is a digital substation. I look at IEC 61850 and as well as the Ethernet fiber network as just components of a digital substation, but not the complete digital substation solution. Next, please. So to start out with, we'll just do a quick comparison between a legacy substation and a digital substation. If you were to visit one of these types of, or both of these types of substations, you'd find some immediate obvious differences. The legacy substation, all the signals and measurements and alarms and so on, everything runs on copper wiring. There are miles and miles of copper wiring. Each of these, a pair of cables is needed for every signal that you need to collect and transmit from the substation. Every one of these signals needs a pair of cables. All these cables have to be terminated, and it becomes just in terms of the installation, in terms of the maintenance, and so on. It's a challenge to maintain. Legacy substations also have large footprints, and that's typically due to the fact that they use separate devices for each function to be performed. Typically in the legacy substation, you'll have a single device, which is a remote terminal unit that collects all of the information from the substation. And that's what you see on the left-hand picture at the top, where all the copper cables are coming into the control room or the relay room at the substation and have to be terminated. All those signals eventually come to a remote terminal unit. And there's limited information available in this type of legacy substation. You basically have access to SCADA information and not much more than that. In contrast, a digital substation is based on the fiber optic network, and the fiber optic LAN basically replaces most of the copper wiring. Up to 80% of the copper wiring is replaced by fiber optic network cables. The reason you can't get rid of all of the copper wiring is because all these devices still have to be powered, and we haven't figured out yet how to run power over fiber cables. The other thing you'll find is that a digital substation has a reduced footprint in comparison to a legacy installation, and that's primarily due, first of all, to the reduction in cabling and cable runs, but also to the fact that a digital substation uses advanced microprocessor-based protection relay devices. And these are very powerful devices that can accommodate multiple functions within a single box. And so they perform multiple roles within the substation, so we don't have dedicated equipment for each particular function. And then instead of an RTU, obviously you still need to collect the information in one central point, and that's the job of the data concentrator. And the data concentrator also typically serves as a gateway that provides information out of the substation upstream to a control center. The other big difference in the digital substation is that it does collect, or is capable of collecting, a lot more information, and that's illustrated by the picture on the right that shows a lot of screens with a lot of different data represented in each screen. Next, please. As for 61850, what is it? Basically, 61850 is a hierarchical, is comprised of hierarchical data models where every device, every physical device is capable of accommodating, again, multiple logical devices. Within each logical device, there's a logical node. Within a logical node corresponds to a specific function that you need to perform at the substation. Logical nodes are comprised of data objects that have attributes or values associated with them. This is in contrast to a legacy protocol that's used in the previous substations. Legacy protocols like DNP3 are index or register-based protocols. And that means that you basically have to create point assignment tables where you list all of the values and measurements that you're making, and you assign an index or a register address to each one. And this is a manual process. It requires extensive engineering effort, and it's also error prone. So typically when you commission one of these legacy substations, you would find errors with the point assignment charts. This doesn't happen in IEC 61850 because the data models, the values are all self-naming and self-referencing. So the values are given sort of a path name that completely defines the position of the point within the station and its function as well. So that's the primary defining characteristic of IEC 61850. The other defining characteristics are the protocols that it is mapped to currently. And those protocols consist of MMS communications. Those are data messages that are sent from the devices within the substation to the data concentrator or gateway to update values at the level of the SCADA information, let's say, for visualization by the station operator on his HMI screen. Then the other important protocol is Goose. Goose is a generic object-oriented substation event. Goose messages are short messages given very high priority on the network. They can traverse the network very fast, fast or faster than the actual copper circuits are able to operate based on relay contact closures and activating other relays. Goose messages can traverse the network faster than that. And because they're given very high priority, and also because there's a repetitive function, they're very high security. There's a very high confidence that the messages will get through the network. And these messages are primarily used for the relay protection functions. And they're basically, Goose messages are the structure within IEC 61850 that actually enables the replacement of the copper circuits with messages on the fiber optic network. And finally, sample values. Sample values are used in the process bus. Sample values are collected by special units called merging units, and they are digitized representations of the PT and CT analog readings that are generated by the instrumentation in the substation. The merging units are directly connected to PTs and CTs. They digitize the analog values for currents and voltages that they are looking at, and they send out data packets on the network representing those digitized values. Next, please. So, since we didn't really like the simple definition of a digital substation as just the IEC 61850 implementation, And since we didn't find an actual definition that we liked, we thought that's a good thing that enable us to create our own definition. So based on what we would like a digital substation to be and what functions we would like it to perform, we came up with this list of features and attributes of what a digital substation should be. So its primary function is to collect and digitize all data that can potentially be of value to the utility. There's some data that we already know exactly what to do with, but there might be other data that we can also collect that we're still not sure what we can do with, but in the future we might figure out a use for it that will help improve operations, efficiency, safety, reliability, and so on. The second thing is a good practice to follow is to digitize data as close to the source as possible. That prevents problems with accuracy and interference and so on. So it's a good principle to follow for a digital substation design. Obviously, a local area network is a critical feature. It's a critical component. The local area networks used to be considered sort of separate systems as a communication system, but now they are an integral component of the digital substation, which is an integrated environment, and a local area network plays a critical role. So this is where 61850 comes in. There are other implementations of digital substations that are not standards-based. Some of the vendors on the market have proprietary solutions where they can still perform what we're looking for at the digital substation, which is collecting and digitizing all valuable data and so on. But these are proprietary solutions. We feel strongly that a digital substation should be standards-based, and that's where 61850 comes in. There are many standard protocols used in the digital substation architecture. We're just listing 61850 and the precision timing protocol. But basically all of your standard networking protocols such as RSTP, SNMP, and so on, those are obviously part of the suite of standards that we're going to be following. The other feature we want to include in the digital substation is that we want it to be highly integrated. We want it to leverage the capabilities of modern IEDs. As a quick example, so emerging units are collecting these sampled values, and they're sampling AC waveforms for currents and voltages at a rate of 80 samples per cycle. So that's 4,800 kilohertz. We can use this information to generate PMU data streams, phasor measurement unit data streams, which are sampled much less, let's say at 180 samples per second, but they can be derived from the sample values. So in the past, you needed dedicated phasor measurement unit equipment to be able to get PMU data out of the substation. Now you can use one device to provide not just the protection, the digitized protection data that you need, currents and voltages, but you can also derive other data streams from it, such as the PMUs. Digital substations should be redundant. Redundancy is important. We're going to show, especially at the process bus level, but overall, we want to, in generally, minimize single points of failure in the design. And because it's so heavily dependent on networking and software, it's critical that the digital substation also be cyber secure and comply with all the NERC-CIP requirements. Next, please. So looking at the typical or simplified substation architecture for a digital substation, we'll just go starting at the bottom with emerging units. We already described that those emerging units connect to PT and CT leads, and they and they digitize the analog signals from the PTs and CTs and place data packets on the network. And once the data packets are on the network, then the protection relays connected to the same network subscribe to particular data packets they're interested in. Not every protection relay wants to see all of the data outputs from all of the merging units. For it to perform a particular protection function, it needs to look at specific PT and CT signals, and it subscribes to those that it needs to subscribe to. Now, couple of things is you see that the merging units use redundant networks. In this case, it's a PRP configuration, parallel redundancy protocol, where you basically build two separate and independent networks, and you use both of them simultaneously. So each merging unit actually mirrors the same message out of two physical ports out of the merging unit, connects each one to its own separate network, and then the protection relays also connect to both networks. So in case that there's a failure of a network component, the network goes down, or the link to that network goes down for some reason, the very important sample values will still get through to the protection relay. So a single component failure will not take down the protection function. The protection relays then in turn connect upstream to a station bus. The station bus is where the protection relays communicate with the data concentrator or the gateway. The gateway usually drives an HMI, and there may also be an engineering workstation, which is used for maintenance and troubleshooting and configuration changes and things of that nature. You'll also see two GPS clocks. And again, the GPS clocks have independent connections to each of the redundant parallel networks, and the clocks themselves are redundant. Turns out that time synchronization is critical to the proper functioning of sampled values at the process bus level. Every sample must have a precise timestamp. So a failure of a GPS clock would basically, if that was the only clock you had, would basically shut down your entire protection system. So again, we need as much redundancy as possible. And actually in the projects that I have done, IC 61850 projects that I have done, we've also made the station bus redundant as well, not just the process bus, but the station bus as well. Next, please. Okay, so why do we need digital substation, or the capabilities of a digital substation? It turns out that substations are sort of key points in the distribution and transmission and distribution grids. And there's this whole effort or movement to modernize the grid, to create a digital grid. And so it's only natural that a lot of the digitalization effort or digitizing effort would be happening at the substation. One other important factor is the changing power grid. The power grid is being modified very rapidly by the connection of renewable power sources, by the proliferation of microgrids, installation of distributed energy resources, and electric vehicles are becoming more and more of there are more and more of them being installed all the time. So this is completely changing the load profiles for most distribution networks, and also at the transmission level in some cases as well. So the changing power grid requires that it creates a couple of issues. One of them is that the protection of the grid becomes much more challenging, because now it's not just the power station that controls all the power flow. There are all kinds of power flows going on in the network because of all these other resources that are being connected. So protection becomes more challenging. And in order to avoid instability and so on, you need to more closely monitor everything that's going on so you are able to control it more closely. And also the fact that we're adding all these new connections and resources also means that we have to be flexible to accommodate those things. So in a legacy substation, if you had to make a change to the substation, you can imagine that would be a lot more difficult than in a digital substation where you basically can connect instruments directly to a fiber optic network. You don't have to run copper cables all over the station. You don't have to change cable routes. You just find a connection point and connect your new instrument or modify your configuration. It's much easier to do that. Now, once you've installed the elements that you need to create a digital substation, we have the infrastructure in place, all the instruments and so on. It turns out that you gain the ability to expand how much data you're collecting. And again, we're looking for all the valuable data available at a substation. So one of the things you get automatically with a digital substation is self-monitoring. So, for example, in a copper circuit that you need to operate in case if there's a fault event, that copper circuit may not have been tested for months and actually may be out of commission and undetected. And when you need it to operate, it's not available. That doesn't happen with digital substation. It's completely self-monitoring. Just as an example, goose messages are constantly being transmitted, even in quiescent states where the station is operating nominally and there are no fault events taking place. Goose messages are transmitted periodically, like once a second and so on. So a device that's expecting to see a goose message, if it doesn't receive it, every second, it will immediately set an alarm, which tells you there's a problem, which means that you can go and fix it and have the circuit operational when you need it. As part of we're also working with the utility on a major program designated sensor deployment program, where again, they're expanding their data collection capabilities by installing things such as transformer monitoring systems for temperatures, oil temperatures, and winding temperatures, for dissolved gas analyzers, station battery monitoring, a weather station, infrared cameras looking at transformers for temperature signatures, and also acoustic and vibration sensors. So all of this entire suite of sensors is being deployed on a large scale throughout the utility. But in many cases, it requires extensive, again, installation of cables and so on, because these are legacy locations that don't have the digital substation architecture already. If they did, it would make this a much easier to do. Next, please. Okay, so looking at a substation, there are many different data signals emanating from the substation, and here we've made an effort to sort of list many of them and categorize them. There are really two main categories. One of them is a real-time data streams. This consists of the traditional SCADA data, but also, again, for the sensor deployment program, we'll also be bringing in all of this extra advanced data collection from transformer monitoring, breaker monitoring, and battery system monitoring, and so on. Also, all the system health information. So again, the system is self-monitoring, so any device failures or changes in device performance, device temperatures, all this information is generated in real time and can be collected and analyzed. Also, another type is CPSM data. CPSM is continuous protection system monitoring, which is a regulatory requirement where essentially we want to be assured that the protection system primary components, such as the PTs and CTs, remain calibrated and sort of follow one another. We can cross-check instrument transformers one against the other. and also monitors the condition of the protection devices and the network switches used to build the station network. So if there's a problem with communications related to protection, all that is alarmed, flagged and alarmed. We also mentioned PMU data. That's another type of data stream. Again, that's automatically available by just leveraging the capability of the advanced protection relays. And then there's video, real-time video from security cameras or infrared cameras. And the other class of data are on-demand files. So the digital substation is continuously collecting data, especially data around events. So it'll collect traces, real-time traces around a fault event and create a file, and that file then becomes available on demand for analysis by the engineering team from the control center. Next, please. So again, we have a physical substation, which is your physical asset. And that substation is controlling power flow, but it's also generating a whole set of data streams, real-time signals that vary over time, voltages, currents, power factors, all of the analog measurements, you're capturing and bringing those in. So think of the substation as a generator of data and information. Next, please. And if you can also take the view that this stream of the real-time data traces with all of the interrelationships between the measurements of the variables and all of the behavior patterns of each one, this all is a representation, sort of a digital representation of the substation itself. So the data that comes from the substation can be viewed as an asset, just like there's the physical substation as the physical asset, but the data generated from the substation it should also be considered as an asset. Next, please. And so if you expand the concept out, then you basically have transformed all your substations into digital substations. You have these data streams coming in from all of the substations. You can aggregate all this data at a central location, such as a control center or a digital operations center. And you do that by setting up a bank of dedicated data servers. Typically, you'll have different data servers for different types of data coming in. Here we're showing real-time video servers, a Pi Historian server, and just a general file server for on-demand information that you bring up, that you call up from the substation. So this bank of servers aggregates all the information, and then you can do some pre-processing and send the information forward to a visualization platform. And the visualization platform then allows you to gives different users access to the information in the format that's most efficient and most usable for them. Besides sending the data to a visualization platform, you also want to do as much analysis of the data as you can. So you'll send all that information to a data analytics engine, and utilities are already beginning to apply artificial intelligence, neural networks, machine learning, and all kinds of sophisticated technologies to perform advanced analysis of the information. And basically what you're doing is you're turning data into useful information. The output of the data analytics engine then can be fed back into the visualization platform, and again becomes useful information that can be routed to the proper users. Here we show some sample applications or uses of the information coming from this digital end-to-end digital utility. One of the applications is just an overview of the system, which you see on the left. Here we are showing you with the red dot, we're showing an event happens at a substation. You're looking at an overview of the system. You get immediate notification of an event that took place. You have a real-time SCADA operator looking at a screen like the single line diagram there. He'll be informed of the event as well. And post event, you can have your engineering team call up and retrieve the oscillography files that completely describe the event and can be used for forensics analysis. Another thing you can do is use the information to create a digital twin. A digital twin is a virtual replica of a physical system. And once you create the digital twin, you can run simulations, you can test changes and new configurations. So the digital twin perfectly simulates the behavior of the object that you're replicating. So in this case, a substation. So if you wanted to make a change to a substation and you had a digital twin, you would first try out the change at the substation and see if that would work or not work, or maybe you'd have to make some changes to your plans to make it work properly. Once you've got digital twins and you've built sort of this data structure, you can also use it for virtual reality training and for providing augmented reality additional information that is layered on real world objects. So you can send a technician to a substation to perform a maintenance task or a repair operation, and you can use remote devices, mobile devices, to call up relevant information and assist him in his work. Next, please. So all of that was under the topic of what we consider sort of advanced concepts around the digital substation. We're looking at another aspect of this as another advanced concept. We are working with Rensselaer Polytechnic and major Northeast utility on a neural network simulator or substation simulator. Our objective is to demonstrate the feasibility of using a neural network to simulate the real-time behavior, electrical behavior of a substation. And as part of this process, we have to decide what type of neural network structure we want to use. That's the job of the Rensselaer students, to figure out the proper network, because there's an entire zoo of different types of networks out there. So we have to select the correct one. And then once we built the network, we have to train it to simulate the substation. And then we have to validate it. Next, please. So very quickly about neural networks, we sort of thought that neural networks might work in this application because even though we're not experts on neural networks, we know a little bit about what they do, and what they're good at are things as pattern recognition and feature identification and extraction, and finding out correlations between data streams. Networks can also be predictive, and they can be used to functionally simulate basically any real-world function. They consist primarily of neurons. The green circles are neurons that are connected by links. These links connect neurons from one layer to the next layer, and the links, the neurons decide whether or not they're activated by summing the products of all the links that are activated incoming to each neuron that are activated, multiplied by a weight. So each link is given a weight. And it is actually the weights assigned to these links that constitute the behavior of the network and the learning. So once a network is trained, the links between the neurons are set, and they determine the behavior of the network. Next. So for a predictive network, and what we want as for the substation simulator is we want to feed it a number of time samples for every quantity that we're monitoring in the substation. So let's say we're sampling every millisecond. We want to feed it 5 milliseconds worth of time samples, and then we wanted to predict what the 6th time sample should be. And we use a recursive neural network to do that, where we feed the output of the network back into the input. Now, a predictive neural network, a recursive neural network, is not limited to predicting only the next time sample of the output of the simulation. You can actually tell it that you want 3 or 5 or 10 or 50 time samples ahead. So this type of structure, this type of network is capable of learning and simulating the substation behavior, the electrical substation behavior, but not just the electrical behavior. There are other data that you can collect from a substation. For example, ambient temperature. Ambient temperature affects the performance and operation of a substation, but it's very difficult to model that in a deterministic electric simulation system, like the one we're going to be talking about that soon. The other important aspect of a recursive neural network is that it can learn and simulate nonlinear behaviors. Next, please. So this project, we start with a model of the substation. We gave that model to both the students at Rensselaer and to the utility that is allowing us to use their RTDS simulation lab. So they created the model to run in the lab, then they ran simulations, and out of those simulations, they generated the data sets or the data streams. Then once the network model was built, we used those data streams to train it and teach it the behavior of the substation. Once the network is trained, we'll run simulations and capture the measurements generated by the neural network simulation, and then compare them with the deterministic RTDS values and validate that the neural network performs as expected. Next, please. And so this is the model that we ran through the simulation. Again, it's the model of the substation. Here we're showing the PT and CT measurement points. We're measuring voltages at the high side of the transformer and also on the station bus, and then we're measuring incoming current and outgoing currents on each feeder. And these measurements are PMU data samples at 180 samples per second. Again, phasor measurement units. Again, we collect all of this information. Next, please. We recorded all that information, then we feed that information into our neural network, and we, once the training is complete, that neural network should simulate the power flows going through the substation. And our inputs into the neural network are controllable loads. So we'll set the loads to certain set points. So we can create nominal running conditions, or we can create conditions where the network is running at near full capacity, just on the edge of full capacity, or we can even create overload conditions. And then we can see how the neural network responds. We can monitor the data traces and make sure that they correspond with the way that the actual substation behaves, or the simulation, the RTDS simulation of the substation behaves. Next, please. If it turns out that we are successful and we can actually get a reasonable result where the neural network does accurately enough simulate the behavior of the substation, then we can do that for any substation, and we can connect multiple substations in the same configuration as they exist in the actual transmission and distribution grid, and create wide area grid simulations. So this is just one application of the idea. Next. And again, that's a very high-level overview. The main takeaways here are, again, that Digital Substation, that its primary purpose is to give us access to all the usable, valuable data in a substation. We really need this kind of visibility into the system in order to meet the demands of the changing power grid. A Digital Substation, if properly implemented, would be able to provide all the current data needs for an end-to-end digital enterprise. And then having access to all the data that we can see through the implementation of a digital substation that enables more advanced applications in virtual reality and simulations, digital twins, neural networks, again, the things that we touched on in the presentation and beyond. Next, please. And that's basically it. So the idea is we need more control, and in order to get more control, we need more visibility, and the digital substation is the solution to give us all the visibility that we need into a substation, and by extension into the operation of the entire grid. Thank you very much.
Excellent. Manny, thank you. Really appreciate your presentation today and you sharing your thoughts and insights on digital substations. It's very informative. Just a reminder to the audience, you can use the chat box in the lower right corner to type in your question, or at this time we invite you to unmute your speaker using *7 if you'd like to ask any questions at this time. So we'll just open it up for any questions. There wasn't any typed in during the presentation, so if you've saved your question until the end, certainly feel free to ask at this time. And I know I had a question, Manny, I wanted to ask initially to get us rolling here. Are there utilities that are currently applying the VR and AR technologies today? Is that something that's currently happening?
Mm-hmm. Yeah, there are utilities applying or beginning to apply most of the technologies we talked about, including AI and neural networks and virtual reality. For example, virtual reality is being recognized as a very effective training tool. So there are a lot of utilities that have already started using VR for training. Of course, if you combine VR again with this concept of digital twins, where you can create a virtual reality version of a real substation, but then in addition to that, you can drive the behavior of that virtual reality substation with real data from the real substation and simulate exactly what happens in the substation, then the training will become super effective. You will basically have hands-on training on every aspect of that substation that you want to build training models for.
Interesting. So we do have a few questions that are coming into the chat. So the first one is, are there redundant servers at each substation?
Again, my personal opinion is that you should build substations to be as reliable as possible, and redundancy is a critical component. I like my approach is typically to, even though it costs more upfront, I think the benefits for the life cycle operation of the substation in terms of maintenance, in terms of reliability and safety and so on, generally justify using redundancy everywhere you can. So yes, there are redundant servers in most of my designs, unless the customer strongly objects. I recommend using redundant components everywhere.
Okay, so we have another question that says, are you aware of any 5G application to replace the over fiber communication from the substation to the control room?
From the substation to the control room, I think there's, especially in the US, there's a great sensitivity again to cybersecurity, and there's a great reluctance to adopt wireless technology in general. That situation may change as cryptography improves and the ability to encrypt information improves the safety of the cybersecurity and safety of the information being transferred back and forth. But I think in general, most utilities have to be convinced that this is safe enough to be used for substation to control center applications.
Another question for you. This is two parts, but I'll read them together. At first it says, what role would virtual reality companies play with the utility providers to develop digital substations? If so, are these firms already aligned with utilities, or are there transferable components from other VR firms, i.e. those doing game design, to marry up with engineering acumen?
Boy, that's a long question.
That first part again? So the first
Yes.
part is, what role would virtual reality companies play with utility providers to develop digital substations?
Well, virtual reality companies are good at building virtual reality environments, and they can basically build any environment to any specification. The thing about virtual reality is anything that you can think of can be done. So the creation of simulated substations for training purposes is an obvious one. We're actually working right now with a virtual reality company that is creating a simulation of a substation, and they have, for example, a training module that shows the technician going through a step-by-step procedure on how to do a bus transfer, which involves closing isolating switches and circuit breakers and grounding switches, and they have to be done in the proper sequence. And the value of that is that, of course, you want your workforce to be properly trained and their training to be fresh. And so if you have a virtual reality environment that you can train over and over again, your skill sets of your workforce remains fresh and immediately usable. And that's very valuable, of course. Second part to the question?
I think you touched on it a bit. It says, are these firms already aligned with utilities, or are there transferable components from other VR firms, i.e. those doing game design, to marry up with engineering acumen?
Yeah, there's, as I said, some work already being done. Utilities are beginning to adopt VR. VR is being used, again, primarily for training. That's sort of the low-hanging fruit for that application. But I believe VR has applications way beyond just the training. And again, this digital twin application, for example, where you can sort of plug in new devices that you want to try out. If you have a digital twin VR visualization that's driven by real data, then you can try out a change to the configuration or try out a new component, see how it works. And again, that's a change beyond the training. You can also do things such as, let's say there's a fault event at a substation, and you've got a virtual reality digital twin of that substation. You can basically replay that fault event in real time through the substation and visualize any of the data or information related to the fault that you want to see. And you don't have to play it in real time. You can play it in super slow motion, for example, where every millisecond ticks by every 10 seconds instead. So you can see very clearly, step by step, exactly what happened during that fault occurrence.
Another question for you. How should we protect those electronics in digital substation from MEP events?
EMP events?
Oh, I'm sorry, EMP. Yes, EMP events.
It's not easy to do that retroactively. It's much easier to design a new greenfield system that's EMP protected. There are technologies out there to do that. Using fiber optic networks is one of the primary ways to do it. All of your electronic boxes, like your protection relays and so on, can be encased in Faraday cages or Faraday type enclosures to protect from EMP. The remaining problem is the power supply circuits. Those have to be copper, of course, and EMP pulses can damage equipment if they come in through the power lines or the power circuits that power these pieces of equipment. Even if they're protected in Faraday cages, they're still electrically connected to the power lines. The technology to address surges on power lines is it uses filters, but these tend to be very expensive filters, and you would need a great number of them throughout the substation. So it's not an easy problem. EMP susceptibility can be mitigated, but at this point, I'm not sure that it can be completely eliminated.
Okay, we just have a few more minutes, and there's 2 more questions in the chat for you. What type and size of server would you recommend for IEC 61850 substation, and how much time data is needed to collect and save?
Let's see. I don't want to really mention specific vendors, but a normal sort of server class Windows machine would be powerful enough to run an IEC 61850 station of even a larger size station. As far as the data collection that you need, you basically want to collect all of the information in real time and save it, not continuously, but at least establish a baseline behavior for the substation. Collect enough data so you've established baseline sort of nominal behavior for the substation. Once you've done that, then you can periodically take data samples over a certain time window, maybe an hour or so, again, to compare that your baseline behavior hasn't changed much. And so you do have the ability to capture continuous data streams. However, as you imagine, the storage requirement will quickly outstrip the amount of data that you have to collect. So what you want to do is start collecting data around unusual events. So capture maybe 30 seconds of point on wave information around a fault, maybe 10 seconds before the fault occurred, and then 20 seconds past the fault. So you encapsulate the exact progress of how that fault occurred. And in that sense, you can almost simulate continuous data capture in the substation.
Thank you. So I'm going to have to defer the last question since we're out of time. Maggie, if you go to the last slide, please. We're going to conclude today's webinar, and we hope that you found it informative. Again, we would appreciate any feedback that you wish to share. So please look for a survey in your inbox. We're asked folks to return it by next Monday, noon Eastern, if you would like to be entered for the raffle drawing. Manny, I'll send you this last question, and perhaps we can get the answer out to Sanjay. But at this time, I'd like to conclude our webinar, and thank you to everyone for attending. Thank you, Manny, for your presentation. Thanks to Maggie for running it behind the scenes. Have a great day, everybody.
Thank you.